Hello, welcome to our talk. What are we going to do today? Quick agenda. First of all, I would like to give an introduction to Apache Kafka, and in particular Kafka Streams. So I guess, who is using Apache Kafka and know Apache Kafka? Almost everybody. Who knows Kafka Streams? A couple of people, not bad, yeah. So for everybody else, we're going to give a high-level overview, so you're not lost in this talk, what's going on here. And then I will do kind of a deep dive and explain how Kafka Streams applications scale. In particular, this is about state handling. And that's important to understand because in the second part, Gwen is covering the Kubernetes, using Kubernetes to deploy those applications. And using Kubernetes, you have certain options how you can deploy an application, and state is a key part. So it's important to understand how Kafka Streams handle state in order to be able to make the right decisions using Kubernetes, deploying an application like that. And in the end, Gwen is giving a live demo, so we hope that works well. And yeah, let's get started. So as you know, Kafka has three main components. There are the brokers, so the Kafka cluster, that is the storage layer in the system. And there is Kafka Connect, that is used to import and export data from and to other systems. And then there is Kafka Streams. And Kafka Streams is a Java library that you use to build stream processing applications. And even if it's written in Java, we also have a Scala API for that. That was contributed in the 2.0 release by Lightband, so we are very happy to now support not just Java, but also Scala in a native way. And, well, you write this application, and then the question is, of course, well, if you have it, you need to deploy it, because it's a regular application. It's nothing special about it. And in this talk, we are explaining you how you can use Kubernetes to do this. And so this application is connecting to the Kafka cluster. It is reading data streams. It's processing the data, so you can filter, you can aggregate, you can join multiple streams, and then it's writing the result back into the Kafka cluster. So let me give an example so you get a look and feel how the API looks like. And this example is the example that Gwen is using in her demo later on. And it's going to be about doing statistics over stock trades. So when we start this application, and I left out a couple of details about implicits and all these kind of things, just like the core thing, you have this streams builder. That's your main, you could say like a factory, where you basically express your application logic. And that's all like lazy, so because it's a builder, so basically you first express your application steps, and then when you're done, you basically kick off the computation explicitly. So when you have this builder, well, first you want to read some data from the Kafka cluster. So you say here, well, please create a data stream. That is a case stream, that's a return type, and reads the data from this topic stocks. And when we have this data stream, now we can start to process the data that is flowing in the stream. And in this example, we would like to compute statistics, so we are having to do an aggregation on top of that. And aggregations in Kafka Streams are always based on keys. And so that's basically the key value model we inherit from Kafka. And doing aggregations based on keys also allows us to scale out the aggregation, obviously, because it's then data parallel. So here we say, well, we want to group the current stream by the given key. And we also apply a time window because, well, a stream is infinite, and doing an infinite aggregation is usually not desired. So you want to chunk the stream into finite pieces. And here we get a window of a size of 5,000 milliseconds, so 5 seconds. And we move the window in 1 second intervals. And then when we have all those windows, well, we apply an aggregation function. That means for every new window we are getting, we are creating a new trade statistics object that is holding our statistics that we want to compute. And then for every record in the data stream or in the window, we call the aggregator function that says, well, we are getting a new trade from the data stream. The key here is not important, so we ignore it. We have the current aggregation result that is stored in the trade stats. And then we just say, well, add the trade to the statistics. And what the trade stat does internally, we don't really care in this example. It's just like adding it to update the statistics. And the important thing here is that this aggregation step is now returning something different. It's not a stream anymore. It's a table expressed in this type K table. And so in Kafka Streams, we have this notion or this concept of stream-table duality, meaning this a stream and a table are the two main abstractions we are providing. And a table is now introduces state. So we're entering the world of stateful stream processing and of stateful applications. And that is why also state handling I'm going to explain later on is so important, because, well, a table is backed up by a local state. So then we can also transform the state actually back into a changelog stream. So for every update, we're getting an update in the output stream. We map the values again to actually do a computation. So here we want to have the average price. And then we write the result back into an output topic. And note, up to this point, it is all just like declarative. It's just saying what we want to do. No computation happened so far. And now, in order to kick off the computation, we are creating this Kafka Streams object that you can think of as a client. We are giving in the builder, we are giving in some properties to configure. So for example, how you can find the Kafka cluster and things like that. And then we call explicitly streams.start, and this will kick off the computation. And now everything is running. So an important part is here is this builder.build thing, because as I said, everything is lazy, and you express this. So the question is, how is this all actually executed in practice?
The code you see here is using the Scala API for Kafka Streams, as opposed to the Java API, which you can also use. The Scala APIs have been contributed to the Kafka project by Sean from Lightband, who's sitting somewhere over in the back. He's saying hi, so we appreciate that. We like being able to write code in Scala.
Thank you. Okay, cool. So yeah, so we're calling this builder.build, and now we want to look into the engine room, how this is actually executed. So this program consists of three main parts. So we have the builder.stream, then we have the group by window aggregate, map values, and to. And internally, everything is represented as a DAG of operators, that what we call a processor topology. And well, for all of those three these steps, we're creating one processor node. So we have a source node, we have some processing nodes, we have a sink node. And well, data is flowing from node to node. So we have data streams connecting those nodes. And as I mentioned, this aggregation is giving us a table. And so for this processor node, we need state that we need to handle. So we also create a state store. So that's a basic thing, but how do we actually now scale an application like that? And for this, we have to look into how Kafka works. And Kafka has this notion of topics that are partitioned. And a partition is a unit of parallelism in Kafka, and that is what Kafka Streams inherits. And in particular, we are representing this in so-called tasks. So let's assume we have an input topic with 4 partitions. And so we can create a task, and a task is running a copy of this processor topology that I just described earlier. And because in this example we're having 4 input topic partitions, well, we're going to create 4 tasks. And each of these tasks is connecting to exactly one partition and consuming the data from it. So it's fully data parallel. And what's also important is, you might be familiar with consumer groups. A Kafka Streams application is actually a consumer group. It uses a consumer. And that is how we can coordinate the assignment from the partitions to those tasks. And that allows us how to scale out. And so in this case, we could have up to 4 threads running in this consumer group. So you can have either 4 instances on 4 different machines, or you have 4 local threads in one machine, each processing one task. And well, so of course, the result is also written back into the output topic. And it's important here, we basically have this, and so also we have state, before I forget this, and state is now sharded. So for each task, we get one shard of the overall state that is representing this k-table that I described before. And it's important to understand that there is this one-to-one-to-one mapping. So we have one input topic partition, we have one task for it, and we have one shard of the state. And that's basically an atomic parallel unit of processing in Kafka Streams. So now with this, how do we scale the application? So let's assume you're starting a new application. Initially, there's of course no state, means the state is empty. And because we have 4 input topic partitions, well, we would have 4 tasks, and all those 4 tasks are assigned to this instance. And during processing, well, now all these instances building up state. And we see I color code this here now with different colors, but it's the same state, it's just like the different shards. Now, when you say, I want to scale out my application, you can say, well, I start a new instance, and based on the consumer group revalence protocols that we're using underneath, those instances get aware of each other, we would reassign the input partitions, and now we would also move the tasks. That means, in this case, we could say we move 2 tasks into the new instance, and in order to preserve correctness, we also need to move the state from instance 1 to instance 2 before we resume processing. So those 2 instances also get the corresponding shards assigned. And note, and that's important, the state on instance 1 is not immediately deleted. We keep it around. And I will explain why we do this later on, but that's important to understand. So basically, we get copies of those shards in instance 2. And now we can even start one more application instance. We do the exact same thing. And we say, in this example, we move the green shard, we rebuild it, and now we're in this state. OK, that's great. Another important thing is fault tolerance. So what is happening if something goes wrong? Because it's a distributed application. And well, the nice thing is scaling and fault tolerance is basically the same thing. Because let's assume we are in this state here. It's a little bit different. I removed the yellow shard from instance 1. And let's say application instance 2 fails. Based on the consumer revalence protocol, this failure would be detected, and we would trigger a so-called revalence to reassign the blue and the yellow partition to different instances. And now we have 2 choices for both. We can either assign them to instance 1 or to instance 3. But now, as you can see, instance 1 already has a part of the blue state locally stored. And that is something we can exploit. So Kafka Streams is doing a little more than the plain consumer. It encodes this information into the revalence protocol. And this helps us to make the decision to say, well, we want to move the task that is responsible for the blue state into instance 1. So we don't need to recover the state completely because we have it already partially. And we would move then for load balancing reasons the other state, the yellow state, to instance 3, where we would first have an empty state that we first need to recover, and then we can start computing. OK, so I talked a lot about like state is moved from instance 1 to instance 2 to instance 3, but how does this actually work? Because as I mentioned, it is local state, and well, there's some magic going on here. And how we do this, I want to explain. Here we have a single instance of a task. We're reading an input topic. It's processed. We have the state and the result topic. So, and in order to make this state fully fault tolerant, we create a changelog topic in the Kafka cluster. And every state update that is done is also written as an update record into this changelog topic. And that allows us to store the state reliably. So basically it means the changelog topic in the Kafka cluster is the source of truth, and the local state can be seen as an ephemeral cache. So even if you write this to disk, writing to disk is not part of the fault tolerance story. The fault tolerance happened in the Kafka cluster, because there the topic is partitioned and also replicated, so you'll never lose the state. And when we need to recreate state, well, we can go to this changelog topic and read all those updates in order to recreate the table. So how does it work in practice when we migrate state? Here we assume we have a single instance with all those 4 tasks. And as I mentioned before, we have this idea of atomic unique units of parallelism, and that is also reflected in the changelog topic. Because we have 4 shards or 4 tasks, we are also creating a changelog topic with exactly 4 partitions. And we do again this one-to-one mapping of this shard is now extended into those changelog topics. So for every shard, we use exactly 1 partition. We don't do like hash-based partitioning or whatever. We just assign it one-to-one and do it manually. So while this application instance is running and is updating the local state, it's also writing all those changes into the changelog topic. Now when we scale out and we create a new instance, and those tasks are reassigned, the first thing this new instance is doing, well, it's going to the changelog topic, it's reading the changes and recreates the state, and after that is done, it goes into processing mode, and now it writes into the changelog topic. So, doing good, yeah. Let's talk about recovery. So, one important thing you have to know about the changelog topic is that it is a compacted topic. Most people are familiar in Kafka with the concept of retention time. That means, well, you store data there, and after a certain amount of time, the Kafka cluster is deleting it. If you would do this for a changelog topic, that would be dangerous, because let's say you have an update for a certain customer that you put into your table. And then this customer doesn't use the application for a certain amount of time, and then it would be dropped from the changelog topic, you would lose this state. It's something you don't want to have. But Kafka not only has topics that can be configured with retention time, but also with log compaction. And for log compactions, there is no concept of retention time, so all data is stored forever. However, for every key value pair, we only preserve the latest entry. Basically, if you have 1 customer and you write like 3 updates into the changelog topic, then the cluster is allowed to garbage collect the older 2s and keep only the latest one. But the latest one is never be deleted. So even if a customer goes offline for a long time or doesn't use your application, you will never lose the state because it's never updated. And this mechanism, when this topic is compacted, guarantees also that the size of the topic is linear in the size of your actual state. Because if compaction is perfect, well, you will have exactly 1 key value per key and no older updates. It also means, of course, if you have large state, if you need to reread this whole changelog topic, you might have high recovery times. And that's also the reason why we want to preserve state in the application for longer locally, so we don't need to go to the changelog topic and reread it. So this state that I described is not just in memory, it's also written to local disk. If your application is offline and comes back, well, it doesn't need to go to the changelog topic because it can just access local disk and say, I have the state already. So for large states, that's usually not a problem. But if you have small states, there is one gotcha that I also want to explain here. So because topics are further divided into segments, or actually topic partitions. And the default segment size is 1 gigabyte. So if you have a large state, let us assume like 20 gigabytes, and you write into the topic, then there is the active segment, that is the newest segment where you append new records, and you have all the older segments. And as long as log compaction is not triggering in, so that's basically a background process on the Kafka cluster, well, you keep appending and appending and appending, and also your changelog topic can, of course, grow a little larger than your 20 gigabytes. But when log compaction ticks in and older segments are removed or basically, well, reduced in size, then if you configure log compaction aggressively enough, you know in average your topic size will be about 20 gigabytes plus this active segment, because the active segment is not considered for log compaction. Only the old segments are compacted. That means if you have updates in the active segment, you can still have duplicates in this changelog topic until the segment is full, and we create a new active segment, and then this garbage collection process, removing old updates, would happen. So for large states, that's not a big issue, but if you have small state, that can actually impact your recovery time. So let's say your state is only 100 megabytes here, and you still run with the default segment size of 1 gigabyte. After log compaction ticks in, it can happen that your overall topic size is still 1.1 gigabyte because the active segment with 1 gigabyte is not compacted. And the rest is, of course, compacted to 100 megabyte, but it means basically that you can have like up to 11 duplicates of your key, and your recovery time is much larger. And we actually have seen this in a customer that had smaller state, and that was kind of, well, our state is so small and recovery takes so long, what's going on? And that was the exact root cause. And we told them to decrease the segment size, and that speeded up the recovery time from like 10 minutes to 30 seconds or something like that. So for small states, that's important. How can you use this? Or in general, so the overhead is proportional as a rule of thumb to segment size over the state size. Means if the segment size is smaller than the state size, then you get reduced overhead. So that is what you want to have. And there are two configurations for that you can use. The size of those log segments, and then also how aggressively you trigger the compaction. That's also configurable. One last thing I want to mention is, though, you should not be too aggressive with those settings. So you don't want to make the segment size too small, because smaller segments is more overhead on the broker side. So there's the sweet spot between like overhead in the broker and recovery time that you need to figure out for your own application. Okay, and now I'm handing over to Gwen, and she's explaining you how you can use all of this within Kubernetes.
Okay, so basically, now we know how it scales in theory, but at the end of the day, you're deploying stuff to production, and how do I actually add more instances and make this thing scale and go up and down in production is a totally different question. And many of us these days run Kubernetes in production, so I'm going to tell you how to do it with Kubernetes. And in order for this to make any sense, how many of you use Kubernetes and totally know what I'm going to say? Okay, I'm not going to bore all of you, only some of you. Kubernetes itself is super easy, so nothing to worry about. It's a database, it's a REST API, and it's a scheduler. So you talk to the REST API and you say, this is my configuration. It's stored in a database, and the scheduler implements your configuration. That's it. You're now all Kubernetes experts. Almost. I'm going to dive into many details. The thing that makes Kubernetes difficult, other than the usual storage and network, is the huge amount of terminology around it. Like everything has a lot of names to learn. So I'm going to walk you through a few names that you need to learn. In general, the basic unit that you worry about is your application. Now your application has some dependency, and it has some configuration, and it has some environment variables, and it has some CPUs that it's going to need. So most of us containerize our application, and we think of the container as the thing we're going to deploy. Not so Kubernetes, which does not think of your application or your container as a thing it wants to deploy. Kubernetes wants to deploy pods. A pod is a set of one or more containers that are always deployed as a single unit. It has storage, which may be persistent or ephemeral, and it has an IP, which is always ephemeral, meaning that you kill a pod, a new pod will start, it will have a brand new IP, it will have brand new storage, and it may run the same application, but for all intents and purposes, it's a totally new thing. Now, one pod is our application, but usually if we think about things at scale, we think about collections of pods because we need our web server to run 50 times or so. And in order to talk about collections of pods, there is the old terminology, which is still very much around, which is replica set. A replica set is basically a way to identify specific pods. For example, all the pods that are running the stock stat application in production, I want 50 of those, versus all the pods that run the other application in dev, and I only need 2 of those. This kind of thing. This is a replica set. That's old terminology. New terminology is a deployment, which is the same replica set, but it also comes with a policy. For example, you are only, when you start them one by one versus start all of them together. That kind of thing. Now, just remember when I talk about replicas, I'm talking about Kubernetes replicas as opposed to the Kafka replicas. We have a lot of replicas all over the place. Now, we talked about stopping and starting those replicas. One of the things that you probably care more than you think you do about how those replicas are placed on physical machines. For example, suppose that I take my Kafka Streams applications and I say I want 3 copies, and by chance or maliciousness, all 3 are placed on the same physical machine. My high availability plan is not as good as I may have wanted it to be, right? I have certain single points of failures in my plan. If I could tell Kubernetes, hey, the pods with this name never ever place all the replicas on the same machine, actually just 1 per physical machine, please, life would be a lot better for me and I could actually have a feasible failover plan in place. This is the affinity and anti-affinity rule. Anti-affinity is place them far, far away from each other. Affinity means these things should actually run together. For example, if you have compute and storage or that kind of thing, you may want them together. Now, there is also a question. I mentioned that IPs are ephemeral, which is kind of sometimes okay, but most of the time our services need to talk to each other. So I have a front end and it has to access the back end. But if the back end only have ephemeral IP, how can I ever find the back end server to talk to? Who do I connect with? So there is the concept of services that basically create a service name, and they do kind of the load balancing and routing behind the scenes. So my front end says, I want to talk to a backend. I have 5 pods from this backend running around as a replica set, and it knows about the ephemeral IP and routes my request. So it's kind of a DNS and internal router and load balancer kind of wrapped into the service concept. Now, this is nice for things when you don't care who you're talking to, but in case of something like Kafka, you probably care deeply about which Kafka broker you're talking to, because Kafka has state. This broker is different from the other broker. This one has a leader for those partitions, and if I want to write to this partition, I need to talk to this specific broker. No other broker is going to do. And when you have this kind of identity where the specific application server that you're talking to also holds the storage that you're interested in, and it has a specific access point, this is where we get to the concept of a stateful set. So there is a lot of different ways to understand stateful set, and the state itself is just part of it. Like the fact that it has storage and it has a persistent volume is nice, but it's not the whole story. The whole story is that each one of those pods, they're no longer random pods. These are pod 1, which is different than pod 2, which is different than pod 3. Each one of them has their own unique IP that I can talk to. Each one of them has its own unique storage that is persistent. Pod 1 always connects to the storage of pod 1, always has the same IP as pod 1. They have their identity. This is stateful sets, which is kind of the core concept of having to manage state inside Kubernetes. Okay, with all this knowledge about how to do Kubernetes, what do we actually do with Kafka Streams? So as you remember, we have those applications, and they each have state. So one may say that, okay, they have state, we may need a stateful set. And this would be a reasonable thing to say. Hey, here's the state in the photo, let's use a stateful set to store it, which is kind of correct, but it's also correct that if it's an ephemeral state, right? If we lose the state, we can recover it. We don't need to take tons of care and do a lot of extra effort to make sure that we never lose it, because we already know the actual state, the durable one, is in Kafka. It's basically a cache. Who cares about caches? And a lot of things have caches, and we throw them away all the time. So you can reasonably say that, hey, stateful sets are kind of a pain in the ass, and we don't need them, and why even bother? But of course, as we learned, if it's a large state, well, it takes time to recover. Do we really need to spend all this extra time recovering the state, where we can put some extra effort into having stateful sets and get to keep it around? This is 100% true, but of course, if you're going to scale in and out a lot, then you're not going to really get advantage of the fact that you have state. You're going to have to rebuild it every time you scale out, and then you lose it every time you scale in. And also, if you're going to have stateful set, well, local storage for stateful sets is still in beta, which means that you'll probably want to use shared storage. If you're in the cloud, if you're in AWS, GCP, Azure, etc., it's probably fine. If it's in your own data center, it's kind of a coin toss. Some of us has fantastic storage admins and fantastic storage, and everything is fine. And the rest of us may have a storage admin that starts an antivirus on my Kafka storage at 3 AM in the morning every Wednesday, and I have to wake up and rescue my Kafka cluster. This may or may not have happened in real life. So sometimes you want to stay far, far away from the shared storage for political reasons. So overall recommendations. No matter what you do, take Matthias' recommendations to heart and try to keep the changelog shard small. It may mean having more partitions in Kafka in order to have smaller state. If you have good shared storage that you can trust, there's no real drawback to using stateful sets. I'll show you, it's not that difficult, just do it. Use anti-affinity, that's important. You don't want to put all your eggs in one physical basket. It will not bode well for your recovery strategy. The other thing you want to use is what we call parallel pod management, which means that if you're going to start our stateful set, do we start one pod after another, or do we start them all at once? If we start one, it will create a state, and then we start another one, it will have to create a state again, and then we start another one, it will have to create a state again. Not a good idea. Make sure you start all of them in parallel, shut them down in parallel. So that's important. And then there is the new concept, I learned about it relatively recently, of disruption budget, which is basically under normal maintenance, how many of those pods are we allowed to take down at the same time, set to something reasonable like 1. 1 sounds like a good number. Just make sure that if you upgrade your Kubernetes, it will shut them down one by one and not all of them together, unless you actually schedule downtime, in which case everything is different. Okay, so this is all cool, but how does it actually work? So I'm going to just walk you through Kubernetes. For those of you who had the pleasure of not knowing, is configured with very, very large YAML files. So prepare for a lot of YAML. And let's start with the deployment, which is stateless. And we basically say, OK, we're doing a deployment, and we are going to call it streams stock stats, because that's the name of what I'm deploying. And I'm going to start with a single replica. I can scale it out later if I want. I'll show you how to scale it out. And basically, I'm selecting pods that have the running application called stream stock stat. I'm creating the pod right here from this template, and I'm saying it's going to have the application called stream stock stats. I'm assigning the anti-affinity, so they're not going to run on the same physical host. I'm running on GKE, so it's not a very physical host, but somewhat physical host. And then I'm basically saying, please deploy this Docker container, which is available on my repo. That's pretty much it. The anti-affinity part is actually much longer in reality, but that's the main idea. And as you can see, it's not super complicated. And it's available on GitHub. Now, if I want to do a stateful set, I start by declaring a service. And in this case, I don't need the IPs, because I'm not going to use them. And then I'm saying I have a stateful set here. Let's run 2 replicas. Start them in parallel, please. And I'm saying I want volumes, because this time I want persistent storage. So please create volumes for me. And please mount them in this path where Kafka Streams expects to see its state. Give them a name. And I want to have 1 gigabyte for each one of those storage volumes. And read-write once means that 1 pod is allowed to access this volume and read and write to it. I don't want, it's not a shared volume, it's specific for each pod. So read, write once right here. And that's about it. Fairly straightforward. I didn't put anti-affinity, but you probably should put anti-affinity. I didn't put the disruption budget because I just found out about it, and frankly, I don't know how to use it yet. But that's more or less the idea, and it's fairly straightforward. So whoever tells you that stateful sets are super complicated, it's probably because he's a storage admin. Yeah, we have Confluent Operator. I'm doing my demo on the Confluent cloud, but if you're running it yourself and running the brokers, you can use Confluent Operator for that, now in beta. And let's see if I can get a demo going. Do I have time for a demo? No, you're not holding it this time. Come on. No, it will be silly. Can you still hear me? Can you still hear me? Cool.
can you see something that looks like terminal? Yes, I think you can. Let's start looking at what Kubernetes is running, which is right now nothing. So let's start running. It's going to be a slightly scripted demo. I'm going to start by running the producer. Basically, just going to produce the trades to the Kubernetes cluster, to the Kafka cluster, so I'll have some statistics to process. So here we are, starting the producer. Let's make sure that we are actually producing something. OK, so you can see this. Basically, I'm looking into the topic, and this is what the trades look like, and you can see that they're coming in. So I'm getting new trades. They have a ticker, they have a price, they have size, they have all kinds of stuff in them. This is nice. The next thing, basically, I want to create my deployment, and I'm creating a stateful deployment, running the YAML that you've all just seen. And now is when I want to see them. So you can see that I have 2 pods, and they're kind of in the pending state. They're about to start. And you can see that one of them is called -0, and one of them is -1. This is how you know this is a stateful set. If this was a deployment, it would be dash long random hexadecimal string and dash something else random. And if you'd kill one of them, you'll get a new random number because it's a totally new thing with new IP and new storage, etc. While here, if I kill stocksat1, I will get stocksat1 back with the same external IP, the same storage, etc. This time, no IP because I didn't configure one. But you get a drift. So at least one of them started, the second started. Let's see if we have results. So let's go to the other topic, stockstats output. Are you crossing fingers for me? Come on, please be processing something. OK, I guess it isn't. One of the things I can look at, oh, here we are, fantastic. So you can see that I have the sum, the minimum, the average price. We have statistics, guys. And I can also go and look at the application, kind of look at the lag, like how far behind I am. And this is a good way to see, as I'm rebalancing and creating new scaling in and scaling out, is it still processing? Am I still keeping up? So let's go back and try to scale it out. So first of all, here you can see my volumes. And now I'm saying, please scale. And now I want 3 replicas instead of 2. So if I go over here, you can see that now I have another one of those starting up. And if I go back here, you can see that it basically keeps going and processing. I still have only 2. It didn't, so I think one of them is still on the way to starting up, but didn't completely start yet. Yeah, it's still creating. Once it gets started, I'll be able to see it scale out. So now it's running. So let's see if I actually have 3 of those. Yes, so now I have 3 of them. You can see that each one of them have a different ID. And you can see that it shrank all the way down. It had to stop, rebalance, and start again because it had to recreate the state. Now, if I go and kill one of them, it will actually start from an existing state. So I'm deleting one of the pods. It's basically identical to crashing it. And it will automatically, you can see it's basically terminated. And now it's starting again. You can see that in this case, it's basically we keep going. Because we don't have to rebalance. We just, or in this case, we may have had to rebalance. But it will immediately pick up the existing state and keep going. So that's about it. I mean, the next thing is just to take down the entire, say bye-bye to my demo and call it a day. So yeah, thank you, everyone. I mean, I think we're out of time. So we'll be around for questions, I think, until the next talk and even afterwards. So thank you. Oh.